Good morning, Michael.
Good morning, Matt.
How good are we?
How good? We've been talking about this. The derivative comes up as the best linear approximation to a function. And we always say best, but we really should ask how good is it, okay?
Well, you've got a picture here, so let's look at it.
And so here I have a function, and you can sort of see the derivative. Oops, this is f prime at x naught. This derivative gives me a straight line approximation to the function, which is pretty good close to here, but as you get further away, it's kind of bad, and it's partly because this thing curves away. So the straight line doesn't tell us anything about curvature, but curvature is important, right?
Yeah, so we could think of, if you wanted to do this and you were in a drafting shop, you'd take a ruler and kind of move it along. So you can see that the tangent moves, right, as it goes around. So maybe we could do something to say where the tangent changes. So we'd have to somehow model that changing of the tangent in order to pick up some of this change of the tangent angle.
So what we can do is we can write down a function that sort of computes that straight line approximation, but at different points t. I'm going to use the t instead of x. Think of x naught and x as being fixed, and we want to figure out what the error is between the value of the function and the value of the straight line approximation.
I think that's an excellent idea, because in a lot of the calculus literature you have fixed points and running points. So we see that t is the running variable in the x direction, and these are, as you said, are fixed values.
Right. So we start at this point t, and we know our linear approximation should, we take the value at t. Oh, I'm going to call this f, because it's related to little f. And then I take the derivative at this point t, and I subtract off x minus t. Okay?
Is that, okay, so x is a particular point and t is a running variable.
Right.
So when x is near t, we're in good shape. But when x is, when this thing gets too big, that means our running variable's moving away. And so if we look at this point here, sitting over here, the error is going to get bigger, the difference between the extension of the tangent and this curved arc.
Right. And so what you notice, for instance, is here, this straight line is a perfect approximation to the function at that point. So if you take f at x naught,
yeah, at x naught.
Oh, no, maybe I'll do this. F at x naught, this is equal to f of x naught plus f prime at x naught. Oh, okay, so let's make sense of this. This looks very familiar because I wrote it down here. So this is actually...
But aren't we going to put an x here?
No, okay, we'll also do, well, let's do both. What happens if I put an x here?
Let's put an x there.
Here I get f of x. And here I get f prime, x minus x is 0. So this guy is here. And this guy is here. So the difference between the two is the error.
Right.
So let me write that down. I'm going to write it down in this order just because I like how it looks. This is the error. Okay?
Yep.
Does that look like something we just saw in the Cauchy Mean Value theorem?
It sure does. We were looking at f of x minus f of a.
Right. And then we had to divide by something. I'm not going to tell you what g is yet. But if I pick a good choice for g, this will work out really nicely. So this is going to give me f prime of x divided by g prime of x. I haven't told you what g is going to be yet, but we know what f is. Can you tell me what f prime is here? Remember, we have a variable t, so we only differentiate with respect to t, and not with respect
To
to
x.
f. Yeah, not with respect to x. So
Okay,
f prime
so-
of t,
Is equal to little f prime,
little f prime of t,
differentiating this with respect to t, we got minus f prime of t.
minus f prime of t.
We
right?
get 0.
But you also have to differentiate this guy.
Oh, yes, we have to do that. We can't just do this. I was just focusing on this. We have to differentiate that.
So this gives what's called the second derivative, which, you know, we haven't really talked about too much, but it's,
But basically, we were alluding to it by the fact that it's the change of f prime. So f prime is at a point is the tangent. So we're looking at how the tangent changes. So somehow it's related to f second derivative because that's indicating how much it changes.
right.
So just out of sort of intuition, is this going to be the way we characterize the error of our...
It is. This is going to come up very closely to the error, but let's keep going through our steps here. So this and this cancels. I got this, and of course I screwed up my mean value theorem. Remember, it happens at a point in
A
between
point
x.
interior between, yeah, so the
Above C.
point C is between those points, right?
So this is equal to f double prime at c times x minus c. Now, here's the trick, Matt. I want to pick g so that when I get a g prime, it exactly cancels that.
Ah, so the derivative of something is linear in C, so we integrate, but we don't know what that is. We'll do it differently. We'll say which function, when you differentiate, is a linear function.
It would be a quadratic function.
And that's pointing in the right direction, right? Because quadratic means parabola,
Right?
and so we stick a parabola, piece of a parabola here, we'll start to get a better approximation. If we neglect it, that's the error, and that's what we're heading to.
Exactly. Now, I want an x minus c. If I differentiate this, the 2 comes out in front.
Yeah,
I don't want 2, so I'm going to put a half here. That way, g prime is t. Oh, I got a minus sign. But that's okay.
yeah.
So here, I have a minus x minus c, because it's evaluated at c. So these guys cancel, and I'm left with minus f double prime of c. Here, I have f of x minus f of x0. And now I'll ask you, Matt, if I plug in x for t, what is g of x?
Well, it's going to be 0. X
0. Okay, that's not good because we don't want to divide by 0, but
No,
we have
got
another
g
term. How about g of x0?
Well, it's right from here, 1/2.
X minus x0 squared. So I can take this, pull it to the other side. The minus signs cancel. So I have f of x minus f of x0 is equal to f double prime at some point c. We don't know what c is, but we know it's the second derivative. And then it's multiplied by x minus x0 squared over 2.
So here we have this, which is the error. Maybe we should write the error on this figure here, exactly those points.
Why do I just call it error at x? Is exactly this.
So here we have this part, the function, and the function that x0 extended on. So
So this difference from here to here,
yeah, let's label it.
that's called the error. Now, the point is, if the difference between x and x0 is a small, like, let's say we're trying to compute the sine of 0.1. This would be, maybe I take x0 to be 0, and x to be 0.1. 0.1 squared is 0.01. Divide by 2 is 0.005. The second derivative of sine, well, it's going to be sine or cosine, but anyways, it's smaller than 1.
Yeah,
So this whole thing is going to be smaller than 0.005. So our error,
it's pretty small.
pretty small.
that's really good. But sine is a pretty smooth function, right? So if we have a function that's more jiggly wiggly, like for example, the Bessel function with a certain value of argument, we get rapid oscillations, then we're not going to be able to do well with just parabola.
So that's because we started with a linear approximation. What could we do other than linear approximations?
Well, we could do a cubic.
Cubic.
We could go on and on
Fourth
and
order,
on.
fifth order, so you can use higher and higher polynomial approximations. So instead of linear, we can try polynomial. And I think that's a good topic
For the next time.
Thank you, Matt.
Thank you.